Professor Lino Amorim from Kansas State University, and he will talk about from categories to Gromov-Witten invariants. Please, Lino, go ahead.
Okay, thank you very much for the invitation. It's a pleasure. So since I only have 15 minutes, kind of try to tell a story here. I will lie a bit, but if it gets too blatant, please stop me. Okay, so let me start with a kind of story, how this goes. That's too much information. Okay, so the idea starts with mirror symmetry. And so there are different flavors of mirror symmetry. So let's start. If you start with a compact Calabi-Yau X, so the mirror, so this double bar here is supposed to be where the mirror happens. So the mirror is supposed to be some other Calabi-Yau, same dimension, X check. And so there are different versions of mirror symmetry. So the kind of original one that got all this mess started was what I'll call here enumerative. And what that said is that there is one can read off, for example, the Gromov-Witten invariants of X. So let's focus on GINA 0. So that's, you want to count the number of curves of a given degree and some number of marked points, and maybe insert some cohomology classes in X, and you get numbers. So those numbers can be computed by computing some kind of period integrals on the mirror. And so the mirror should come in a family, and you have some sort of holomorphic volume form because it's Calabi-Yau, and you integrate that, and you again get some numbers, and those numbers correspond to Gromov-Witten invariants. So later on, Kontsevich came along, and he proposed this, what we call homological mirror symmetry. And he said, so other things should hold is that some categories should be derived equivalent. So for X, if you take the Fukaya category of X, so that's a category that only depends on the symplectic structure on X, and objects are, roughly speaking, Lagrangians in X, should be derived equivalent to some, so this DG here stands for DG enhancement, you can ignore that, for coherent sheaves in the mirror. Okay, so these two categories should be derived equivalent. So then people generalize this, so let's say if X is Fano instead of Calabi-Yau, we still should have some sort of mirror symmetry, but now the mirror is not just some other Fano manifold, it's just maybe some space which will be non-compact, and together with a holomorphic function defined on it. And then to get mirror symmetry, you have to, so in the non-Calabi-Yau case, mirror symmetry is less symmetric. So you have to change one of the sides. So instead of just looking at these period integrals, there's this theory of primitive forms, which is this theory that studies like the unfolding of the singularities in X of the function W. And then you have to replace coherent sheaves on X check by matrix factorizations of W. Okay, so this is a generalization of category of coherent sheaves that keeps track of the singularities of this function W. Okay, so if you want to have just one example in mind, and we'll be focusing on this case where it's Fano, or it doesn't need to be Fano, but not Calabi-Yau. So we can take, if X is just projective space, CPN, then the mirror, so the space underlying is just complex torus, C star to the N. And this function W is just this Laurent polynomial. Okay, so there is this Q here. This is some parameter that has to do with the choice of the symplectic form on CPN, kind of rescaling it. But this is kind of the thing to have in mind. Okay, so when Kontsevich proposed this homological mirror symmetry, he also proposed that, in fact, homological mirror symmetry should be strictly stronger than the enumerative one. Meaning that if by some reason you get to prove homological mirror symmetry in some case, it should be kind of formal consequence of that enumerative mirror symmetry should also hold. Okay, so what's the idea here? So all these categories that I showed above, so this Fukaya category, coherent sheaves, matrix factorizations, with these assumptions are all examples of what were called Calabi-Yau infinity categories. Okay. Or DG categories, if you prefer, kind of more or less same thing. And so the Calabi-Yau part means they have some sort of trace map that they satisfy some sort of either Poincare duality or Serre duality, depending on how you want to think about it. And the things On the enumerative side, so this Gromov-Witten invariants, period integrals, all these primitive forms, they all determine Frobenius manifolds. Okay, so all this information of Gromov-Witten invariants, at least in genus 0, can be encoded in what's called a Frobenius manifold. So that's like a space. Usually it's not a very interesting space. It's like a vector space or a formal space, but that has a flat metric and a product structure on the tangent bundle, such that when you put the metric and the product together, they are a Frobenius algebra at every point. Okay, so to realize this proposal, right? So what do we want? So we want a machine that eats these sort of infinity categories and spits out Frobenius manifolds. Okay, that would be the hope. And the idea is that, so when you feed it the Fukaya category, you hope that what you get on the right side, the right-hand side, is the actual usual Gromov-Witten invariance of the space, the symplectic manifold you're considering. Okay, so that's why, so I'll call this non-commutative Gromov-Witten invariance, because I don't know, it sounds fancy. Okay, so in fact, to actually go from one box to the other, there's a middle step. So we'll do this in 2 steps. And so the middle step here is what's called the variational semi-infinite Hodge structure. Okay, it's kind of a very complicated name. So this notion is due to Baranikov, and I'll try to explain how to get it. Okay, so variational semi-infinite Hodge structure is basically some sort of module over a ring of power series. We have this formal power series, and then we'll have kind of a flat metric and a pairing in there that will have the kind of expected compatibility relations. And out of that, there are ways to produce Frobenius manifolds. Okay, so how do we get one of those in these cases? So we have to look at Hochschild invariants of these sort of categories. Okay, so if you don't know what these things are, kind of there's no hope of telling you what they are in this brief amount of time, but I'll just try to make an analogy. Okay, so if we think on this space, your category is some sort of non-commutative space. Okay, the analogy is that, so we have all these invariants: Hochschild cohomology, homology, negative cyclic homology, and so on. So the analogy that they usually think on is Hochschild cohomology are like vector fields, homology are like differential forms, and negative cyclic homology is like the de Rham cohomology of our space. Okay, they play those roles, and they have many of the same formal properties that these things have. So there are Lie derivatives, you can contract differential forms with vector fields, there are Lie brackets, all those things that we have for usual vector fields and differential forms. Okay, so these things exist in basically all of these categories, but there is one thing that we have to assume or prove in each specific case, which is this Hodge to de Rham degeneration. Okay, so usual Hodge to de Rham, right, says that in a Kähler manifold, the de Rham cohomology of our complex manifold is given as just this direct sum of the Dolbeault cohomologies. Okay, so here there's this analogy. So this was proposed by Kontsevich and Soibelman, that we should have in this, for this sort of saturated ones, actually just proper and smooth is the important thing, this negative cyclic homology should be kind of given just by the Hochschild homologies, just adjoining this extra variable u. Okay, and so this is conjectured to be true for all of these proper and smooth infinity categories. This actually has been proved by Kaledin to be true for Z-graded ones. So the ones we are interested are not Z-graded, they're just Z-mod 2 graded. So for us, this is not proved, but in our case that we'll consider, this is actually kind of trivial. So we don't need to worry too much about that. So if we have this Hodge to de Rham degeneration, so what do we do next? So what we do is we take our category, C. So again, we should think on this as like some complex manifold. And then we take a Versal deformation, okay? So we take this family parametrized by Hochschild cohomology, okay? So this should give some nice, smooth, actually treated just as formal family. And then we take the negative cyclic cohomology of this entire family, okay? So this is, in analogy, what you do with a complex manifold. We take a deformation of the complex manifold, and then we take the cohomology of this, or relative cohomology of this total space, and then in there, we have two important structures. One is we have this, I use this get here, this is Getzler. So this is an analogy with the Gauss-Manin connection. So when you have a deformation of a complex manifold, as smooth manifolds, they're all the same. So there's this connection, the Gauss-Bonnet connection. So there's a similar thing here. And there's also a pairing. So this is called higher residue pairing, which is in analogy, like I said, right? This is supposed to be cohomology. And on cohomology, we have a pairing, right? You can just integrate over the space. Okay, so in these three things, so a flat metric and a pairing and a lot of compatibilities between them is what's called a variation of semi-infinite Hodge structures. And this is what we have on the negative cyclic homology of this deformation of our initial category, assuming we have this Hodge to the round. Okay, so once we have this, what do we want to do? Okay, so what we need, and this is the idea due to Saito, although I didn't do it in this context, but the idea is that what we need now is a primitive form. Okay, so a primitive form is just an element on this negative cyclic homology that has kind of a long list of properties that is very hard to state, but kind of the main idea is that when you differentiate, using the connection, when you differentiate this, you should think on this in kind of volume form in the direction of all vector fields. So this, you should think on this is like tangent space to the base of our deformation. We get an isomorphism. Okay, so we get basically the entire cohomology or homology action. Okay, so and then there's like a long list of properties that we need. And if we have one of these primitive forms, there is like a canonical way to construct a Frobenius manifold on the base of our deformation, the deformation space. So the idea is that what we need is to figure out which primitive forms we can find, or even if there are some. Okay, it's not obvious that they exist. Okay, so the kind of main theorem that we proved is in this case. Okay, so if our infinity category has its Hochschild cohomology, so this is a ring, and if it's semi-simple, if it's just direct sum of fields, that's the conditions we are working with. And then this Hodge-Schuderman degenerates, and there is a bijection between the space of primitive forms that have a kind of a specified value at the origin. Okay, so what this one is, so the Hochschild cohomology as a unit. So then we dualize it and we send it to Hochschild homology because it's Calabi-Yau, and that gives us a special element on Hochschild homology. And that's what our primitive, the value of our primitive form should have at kind of the starting point. And so such primitive forms are in bijection with gradings on Hochschild homology. Okay, so this is just a linear algebra thing now. So we have Hochschild homology. This thing comes with a pairing, which is called the Mukai pairing. And this grading is just an antisymmetric operator with some couple of extra conditions. Okay, but it's a matrix. That's the point. It's a very simple linear algebra thing. Okay, so, but in general, there are many choices of gradings. Okay, so the conclusion here is that this machine is not as good as we hoped for in the beginning. So it does not depend only on the category. It needs on the choice of this primitive form, which in this case is equivalent to the choice of this grading operator. Okay, so this kind of numbers, non-commutative Gromov-Witten invariants that we end up with depend on this choice. So they're not just an invariant of that. Okay, so of course the natural question is, okay, so what if the thing you start with is the Fukai category, right? We want to end up with the usual Gromov-Witten invariants of the space. Okay, otherwise this would be some kind of categorical mess that no one would care about. So the point is that we have to pick the correct grading operator. And there is a way of doing that in the case of the Fukai category, because for the Fukai category, there is a map called the closed open map, which is usually an isomorphism between the cohomology of our underlying space and this Hochschild cohomology of the Fukai category. Okay, and then what we do is on cohomology of X, there's of course an integer grading, and so we can use this isomorphism to pull it back to a grading on Hochschild cohomology, and then by dualizing it on Hochschild homology, that has all the properties that I put the ... above. Okay, and then the theorem is that in this case, if we pick this grading, these non-commutative Gromov-Witten invariants do in fact give the usual Gromov-Witten invariants of X. Okay, so in this case, we can use this to prove kind of mirror symmetry statements automatically from homological mirror symmetry. Okay, and because I'm out of time, let me just tell you like one set of examples where this theorem applies would be for compact toric manifolds, not all of them, but the ones for, so this condition of Hochschild cohomology being semi-simple can be translated into this Hori-Vafa mirror of the toric manifold, if you know what that is, being a Morse function. Okay, so it is that the semi-simple is equivalent to this having non-degenerate critical points. Okay, so if X is toric and Fano, this is true for a generic toric symplectic form. If it's not Fano, then this theorem would still hold as long as this thing is Morse, but it'll be harder to check. Okay, so let me stop here. I'm out of time.
Okay, thank you very much, Lino. Well, I imagine that questions might work through the chat or the questions and answers that I have here, but I don't see any questions. But I would like to ask one, at least one, but so this applies, so you meant, so a little bit higher you had Calabi-Yau.
Yeah, but there, so there are two meanings here.
But then you have general symplectic manifold on.
Yeah, so there's two meanings for Calabi-Yau, right? There's like the space being Calabi-Yau, and there's the infinity category being Calabi-Yau. And for the Fukaya category to be Calabi-Yau, it basically holds for any compact symplectic manifold.
Okay.
The idea is that we want to have kind of Poincare duality on Floer cohomologies. And as long as you work with compact Lagrangians, we always have that.
Okay.
Unfortunately, there's these different meanings for Calabi-Yau. Okay. For coherent sheaves, this is true. The category of coherent sheaves is Calabi-Yau if the space is Calabi-Yau. But on the A side, it just means compactness.
Yes, these theorems of your theorem with the two applies to any a priori any compact symplectic manifold with that semi-simple condition.
Yeah, so that kind of restricts a lot. So if you think about it, so because of this thing,
for toric manifolds, say for example, for toric manifolds, which I'm more familiar with, how restrictive is that condition? So does this make any sense? Does this say anything new for four-dimensional toric symplectic manifolds, or you go to higher dimensions? Or?
No, I don't think so, right? So the idea is here that this isomorphism here, so I'm talking about isomorphism as just as vector spaces, but if you work with rings, right? So the ring structure on Hochschild cohomology matches the small quantum cohomology on X. So the statement that this is semi-simple would be saying that quantum cohomology is semi-simple. Okay, and that's, for example, for Fano things, that's equivalent to this Hori-Vafa mirror being Morse. And that for Fano things, I think this is known to be true generically. For a generic symplectic toric form, this will be Morse. If you get outside the Fano case, I don't know if this is true, but then what is probably true still is that if you deform the Fukaya category, so if instead of working with small quantum cohomology, you deform in some direction on big quantum cohomology, it's probably still true that like generically, this is Morse. Okay. So if you deform also the quantum product, this is probably true generically. But in the Fano case, it's enough really to just deform the symplectic form. More generally, you really have to deform the quantum product in this more complicated way. But I don't think that has been proved.
I have here a question from Gonçalo in the chat, asking, in the example of deformations of complex structure, what do these primitive forms and gradings correspond to?
Yeah, so these gradings here are kind of only make sense in this semi-simple case, or at least they are only seem to be relevant in the semi-simple case. And with the primitive forms, there is like a actual, so it's kind of the other way around. So these categorical versions of primitive forms is basically just copying the Saitos primitive form, which are these things to study the unfolding of singularities. So in Saito theory, right? So he has this, you unfold the singularities, and then you have this, you have to pick these kind of primitive forms to get these numbers, okay, or this Frobenius structure in the way we talk about it today, not when he did it. And then, so there's a middle thing here where these primitive forms, so there's a middle, in the middle of this bijection, there's a middle one, which would say that these primitive forms actually correspond, and this is much more general than the semi-simple case, correspond to these splittings of the Hodge filtration. Okay, so up here, I told you this is supposed to degenerate here. And in general, there is a map in this direction from negative cyclic to Hochschild, and this picking this primitive form, or in fact, this splitting is like picking a splitting of this map. Okay, that's kind of the more the geometric situation where this is kind of basically one-to-one is in the case of this studying singularities, where this is basically this Jacobian ring, or dual to the Jacobian ring, the Hochschild homology, and this negative cyclic is this twisted de Rham complex, and you're kind of splitting that. That's what this means. I don't know if like geometrically there's a very good understanding of what that is, but it's splittings of this twisted de Rham complex by the Jacobian of this W that you're working with.
Okay, thank you very much, Lino. So let's move to Pedro Boavida. Maybe Lino, you can stop sharing, and then Pedro will start sharing.
Share the screen.
Okay, so our second speaker today in this parallel session, geometry parallel session, is Pedro Boavida de Brito. He's a postdoc at the moment here at the Center for Mathematical Analysis, Geometry and Dynamical Systems of Técnico in Lisbon. And he's going to talk about finite type invariants, embedding calculus, and Galois symmetries. Go ahead, Pedro.
Okay, so thank you. I'd like to begin by thanking Miguel for giving me inviting me to talk about my work here. So the title is very long, and there's not much time. So my plan for today was essentially explain the title and maybe tell you a little story of how these three things come together. So I'll start with finite type invariants. They're also called the Vasiliev invariants, and there are certain invariants of knots. So we'll be looking at knots, usual knots. Here they're long, so they're just embeddings from the interval to the three disk, and they will be standard near the boundary. Okay. So we can look at isotopy classes of such, and they form a monoid by concatenation. It's an abelian monoid. So the Vasiliev invariants are a large class of invariants of knots. So the setup is the following. So you take an abelian group, and then you look at invariants, so just monad homomorphisms from these isotopy classes to that abelian group. And one such knot invariant is called degree n or type n. If the following holds. So if you take any knot which is singular and has n+1 double points, and you resolve this singular knot, so a double point is something like this. Locally it looks like this. So if you resolve all the double points in all possible ways, you get, I guess, 2 to the n+1 non-singular knots, and you evaluate your invariant on each of these with a sign. So you take the product of the signs corresponding to each double point, whether you resolve it one way or the other, and you just take the sum of all of these, and that should be 0. Okay, you should think of this as something like an invariant which is sort of polynomial of degree n. So for singular knots, with n+1 double points, it's sort of, if you resolve in all possible ways, then you get 0. So there's the first few cases, the first few degrees, they are trivial. But already if you look in degree 2, it's easy to see that you get a non-trivial invariant, and it's actually determined on the value of the trefoil knot. But that's, okay, not much, but there's some important results that tell you that actually this class of invariants, it's very large. So for first, there are non-trivial invariants of any degree. And then they are at least as strong as all the sort of quantum knot invariants. So there's many of them, okay? So the big result about Vasiliev invariance is the so-called fundamental theorem. That's due to Kontsevich, and there's a different approach, similar but different approach by Bott and Taubes. Which roughly says that there is a sort of universal invariant. Okay, so there is a degree n invariant, which is universal in the sense that if you take any other complex valued degree n invariant, then it factors through this complex vector space. Okay, so this complex vector space here is essentially the vector space generated by certain diagrams called Feynman diagrams of a certain degree. So here there are some examples of such. So that you have this blue line which corresponds to the knot, and you have some univalent vertices which are on the blue line, and then you have some trivalent vertices which are sort of outside of the blue line. And each of these elements, so given one of these diagrams and your knot, you can take a certain integral, and that produces a number, that gives you a number, which is sort of the coefficient of this diagram in this Kontsevich integral. Right, so this is a classification in the sense that, as I said, that all the type n invariants, they factor through this. In particular, they are the complex value degree n invariants, or maybe rational value degree n invariants. They are essentially functionals on this vector space. Okay, this is just a dual construction. So it gives you a classification of all invariants. So there's quite a few things that are known about these vector spaces, but we still don't know, for example, their dimensions. So we know that they sort of grow very large, but we don't really know their dimensions. We don't even know that whether this group, the abelian group that you of Feynman diagrams, whether it's torsion free or not. Also another thing that we don't know is whether they really, well, they seem to be very abundant, but we don't know whether they actually are complete invariants, so whether they're enough to distinguish knots. But the thing that I want to talk about today is a different question, which is whether there is a version of this Kontsevich integral, so one universal invariant which works over the integers, okay, which classifies integer valued invariants or invariants in any abelian group. Or maybe a slightly simpler question is whether there is an invariant with values in the p-local integer. So you can look at the prime and try to ask that question for a prime. So this approach of Kontsevich, both Kontsevich and Bott and Taubes, these integrals are given by configuration space integrals. So they cannot really give you an answer to this question. Okay, so you need a sort of, first you would need an integral, like a candidate integral, and you cannot do this using usual like configuration space integrals. So I want to briefly tell you about a candidate for this, an approach for this, and that comes through embedding calculus. So very roughly, the idea is you want to scan your knot or by points. So this is part of a general theory, and I'm going to focus on the case of knots because that's sort of the simplest and the one that we understand a little bit better. So, so if you have your knot F, you can just evaluate that knot on points, on finite subsets. So you get a map from the interior of the n simplex, which parameterizes these finite subsets, to the space of configurations of points, of endpoints in R3. Okay, so that's just usual evaluation. And it requires some work, but you can show that because F is a smooth embedding, you can actually extend this evaluation map to the whole of the boundary of the simplex. So the boundary corresponds to points colliding on the interval, right? So you have to, you're adding the boundary to the simplex, then you also have to enlarge the space of configurations a little bit to sort of keep track of directions when points collide. So that's this bar here. So that's a certain compactification of the space of configurations. Okay, so you embed this, you include this space in a larger space, and you take a sort of closure that allows you to keep track of sort of collision directions. So I want to maybe briefly give you the first two instances of this invariant. So the first one is n equals 2. That's really quite simple. So you have 2 points, right? And the images gives you this configuration of 2 points in R3, which are, well, essentially specified by a direction. So that's a point in a 2-sphere. So that works well when these 2 points are distinct. But when these points come together, you can still, you can take the derivative of F, which is non-zero because F is an immersion, right? So you have really a map from the whole of the 2 simplex to the 2-sphere. The only boundary conditions that you have are when both of these points are endpoints, because you have this condition on the endpoints. And that's essentially shows that because you really have not much boundary condition, all these maps are essentially null homotopic. So the n equals 2 invariant is really very easy. There's no invariant. But the next one, n equals 3, that's a little bit more interesting. So now we have a map from 3 subset to this compactified configuration space. And it turns out that essentially because the n equals 2 invariant is so, the restriction to 2 points is so simple, you can show that in fact you can deform this map so that its image lies in the subspace of the configuration spaces where 2 of the points are fixed. So that's this x and y. These 2 points are fixed. So essentially you get a map from the 3 simplex to this space, this wedge of 2 spheres, and if you look at homotopy classes of these maps, you get an invariant, right? So that's an invariant with values in this third homotopy group of this wedge of 2 spheres, which is very known classically. So it's generated by there's 3 generators. There's 2 corresponding to the 2 Hopf maps. And there's the third one, which is essentially the Whitehead product of the 2 inclusions. And you can show that actually the image of the trefoil corresponds to exactly the Whitehead product, this Whitehead product. And in fact, there is this result by Badnikon and Scannell and Sina that says that this map is actually the degree 2 invariant that I mentioned at the beginning. Okay, so it's actually the unique degree 2 invariant, which is also some coefficient of some polynomial that appears in knot theory. So the higher invariants, so this is up to degree 3. The higher invariants are much harder, but there are some things that we know about this map. Okay, so this is the map from the knot space into the space of stratified maps, these evaluation maps. So we know that the target, when you look at the components, that it's a finitely generated abelian group. And we know that this map respects the concatenation, so it's a monoid map. More recently, it was shown that it is a degree n invariant. Okay, so it's at least it's a candidate for the Kontsevich integral. It's an invariant of degree n. So the definition that I gave you of Vecellin invariant doesn't make this clear at all. But there's sort of other geometric ways of thinking about this invariance, which allows which makes this theorem a little closer. So the conjecture is then, well, maybe the embedding calculus, so maybe this map is universal over the integers. So we cannot really quite show this, but what we can show is the following. So if you fix a prime p, you can just tensor this finitely generated abelian group with the p local integers. Okay, so you invert everything but p, and you look at this evaluation map, and we could show that it's a universal invariant of degree n in this range. Okay, so as the prime gets larger, you get a better and better invariant. And it also follows from this that actually the p local, so the p local valid invariants of degree exactly n are just like in the Kontsevich integral. They are like duals, ZP duals of this ZP module of Feynman diagrams in the same range here. And in fact, it's not completely, you cannot really deduce it directly from this theorem, but from the methods, you can show that, in fact, you get universality over the rational numbers as well, without any restrictions. Well, essentially, you get, the embedding calculus gives you the, like, it lifts the Kontsevich integral, okay? So it gives you, at least as much as the Kontsevich integral. It might give you more. So it might give you more. And that's also why I should say that we don't really know much. We don't really know about the torsion of these abelian groups. So it could be that this theorem is saying that all the invariants that we get here are really just lifts of the rational invariants. But it could also be that there are really new invariants and torsion invariants, and they would not be detected by the Kontsevich integral, but they would be detected by embedding calculus. So do I have one more minute?
Yes, one, yes.
Okay, so I'll give you a very, so in some sense, so this embedding calculus, it's more general, and it's a more general method than for knots. And also the sort of argument that we use is I think it's could be used in other settings. But so let me just tell you very briefly what the idea is. So there is this evaluation map, and you can vary the cardinality. So you get a tower of spaces, and you can look at the spectral sequence associated to the tower. And there's this it's important result of Kozanovic that says that essentially, if you want to prove the conjecture that the invariant is universal with the integers, you have to prove that the collapse at A2 page. So we look at this P completion of the tower, and then it's something amazing that happens, that when you P complete the tower, you get a lot of automorphisms. So in fact, you get the absolute Galois group acts on the whole tower, and using all these automorphisms, you can show that. So you get a lot of structure on the differentials, and you can show that essentially that's enough to show, just like by the very easy part of this action, you can show that in fact that you get a lot of differentials collapse, and that's how you prove the theorem. And yeah, I think I'll stop here.
Okay, Pedro, thank you very much. We have some time for questions. Well, I don't know how the participants ask questions. I don't see them asking, But I do have another question, because you know, these Vasiliev invariants appeared in the early 90s. I was a graduate student at Stanford, and we had lots of working seminars at the time between graduate students and professors discussing these type of things that appeared, and they seemed to be magic at the time. They would solve. Yeah. They seemed that people expect they were going to solve the problems of classifying knots. Let's say in a word. And another thing that just to put some context, Signa that you mentioned there, is that Dev Signa?
That's Dev Signa, right? Yeah.
So he was my colleague then. I have heard from him for a long time. He bought my car when I left Stanford, by the way. Okay. Anyway, so the point is, I thought, you know, I think so this was 93, 94, so it's almost 30 years now. And for, I guess, 20 years, I didn't hear more about Vasiliev invariants. I thought that the subject had kind of cooled off. I still followed the Kontsevich and the Tao about the approach. And I think there were then 15 years or something where nothing happened. Dror Barnatan, I remember he was giving talks all the time about this.
Yeah, yeah.
But it seems that from what your talk, that there in the results you presented, that in the last 4 or 5 years, things starting, people started looking at finite type invariants. Am I correct, or I just didn't pay attention? The subject died for a while in his...
Well, I mean, well, I'm not an expert on finite type invariants, so I sort of landed in this story by... So I was looking at this tower of spaces and for knots, and then we realized we learned about this connection to finite type invariants, and then we could use sort of these symmetries to prove this result. But I think in fact, as you say, there was like a lot of activity in the 90s, in the early 90s. A lot of things were proved then. And then, I mean, I think finite type invariants, they also developed into not just for knots, but for example, for 3 manifolds, and it sort of developed in that direction. As you know, there's papers, there's papers, for example, from mid-2000s by Barnatan and others, where they, for example, compute the Kontsevich integral of the N naught. That was a big feat. But I think there were maybe it decayed a little bit after.
Okay.
And this approach is sort of more homotopical, so it could only have appeared now, you know, in some sense, because that's when also these tools were sort of better understood. I mean, Dev Signa was thinking about the case of knots for a long time, I should say. I mean, he was also one of the, you know, people that were studying embedding calculus. They were sort of studying general embedding spaces. He was really just thinking about knots for a lot. But you know, there's some new developments that are more recent that have sort of contributed to this.
Okay.
Yeah.
Thank you, Pedro. Thanks for this talk that made me recall good times from a long time ago. Okay. If there are no more questions, please let's move on to the third speaker.
That's me, right?
That's you, Gonçalo.
Shall I share my screen?
Yes, please.
Yeah. Okay, here we go.
Okay, so third speaker today is Gonçalo Oliveira. He's from the Universidade Federal Fluminense, and he's going to talk about special Lagrangians and Lagrangian mean curvature flow. Go ahead.
Okay, thank you very much for the invitation to participate. So I'll be telling you about some joint work with Jason Lotte, but really what I'll be doing most of the time is motivating this problem using an example. So, but the general setup is the following. We have a symplectic manifold, 2n-dimensional, and a Lagrangian submanifold of it. So we have a symplectic form, omega, and remember a Lagrangian submanifold is one for which it's an half-dimensional submanifold on which the symplectic form restricts to 0. And it is common to regard symplectic manifolds up to a notion of equivalence known as Hamiltonian isotopic. And we will see in the example what this what this Hamiltonian isotopy means. But maybe if you think of a symplectic manifold as a generalized phase space of a mechanical system, and the Lagrangian submanifold as a generalized configuration space, then Hamiltonian isotopic Lagrangians are somewhat equivalent sets of initial conditions for your mechanical system. You can more or less think of it that way. And I will denote the Hamiltonian isotopic class of a Lagrangian by straight brackets L. And then some natural questions appear. If you think of Lagrangian submanifolds up to Hamiltonian isotopic class, which is whether there is a canonical representative of an Hamiltonian isotopic class, whether it is unique in case there is one, a canonical representative, and if it is unique or even if they are not, how can you find it or find them, right? So those are natural questions that arise, and I'll illustrate possible answers to these questions with some examples, or with one particular example, which I'll keep running. So which is the case of the two torus, which I'll think as R2 mod Z2, and I'll think of the square model where you identify opposite sides. And we have the symplectic form coming from R2, which is the X wedge dy. And secretly, you can also think of the metric in R2, the flat metric on R2, the Euclidean metric on R2. Then I've drawn here three torus with three different Lagrangian submanifolds. And in dimension 2, remember that the Lagrangian submanifold is half-dimensional, so it will have to be one-dimensional, so it's going to be a curve. And then the condition that the symplectic form restricts to 0 on it is immediately satisfied. So any curve is a symplectic submanifold. And I've drawn here several circle Lagrangians. So they are all circles because they start and end at the same point, right? So this point here is the same as that point in the torus, as are these points here and these points here. Well, this last one, they got a little, the square got a little off where I had initially placed it, but anyway. And so we have the yellow ones and the blue ones. And the condition that they are Hamiltonian isotopic is that the signed area between them vanishes. So that means that the area in blue, which is where the blue curve is on top, is the same as the area in yellow, which is where the yellow curve is on top. And then I may ask you which of these, for each of these pairs of Lagrangians, of Hamiltonian isotopic Lagrangians, for which of them you have a canonical one? Which one of them is canonical, somewhat canonical? And we could argue that the straight lines seem to be more canonical than the other infinite possible examples. And so if we want, and then if you accept that answer, and if we want to generalize the notion of a straight line to higher dimensions, we need to find the characterization of straight lines. And the characterization is what I've given you below. So we will consider the complex number Z, which is X plus IY. And then we have the one form dz here. And we restrict it to L. And if you restrict dz to L, and you call S the arc length parameter, so that must differ from the S by the component of the velocity of the curve in the X component plus I times the component of the velocity in the Y component. So that's a unit complex number whose real part is the velocity in the X direction and whose imaginary part is the velocity in the Y direction. So this beta needs to be the angle that the velocity makes with the X-axis at mod 2 pi. Okay, so mod 2 pi. And then, of course, being a straight line simply means that this angle is constant. That means that the velocity in arc length parameter is constant. So that's a characterization of a straight line. And this we can generalize to higher dimensions, this notion. And then, but before we go there, let me address the other question I asked, which is, okay, and how can you go and deform an initial Lagrangian to the canonical representative of its Hamiltonian isotopic class? In this example is, how do I deform any curve to an Hamiltonian isotopic straight line? So I've drawn here the curve in blue, which you want to push out in this direction, which I signaled here. which is basically the direction of its curvature. So it's the second derivative with respect to arc length parameter. So what you want to do is to find a one parameter family of curves parameterized by the non-negative real numbers, which evolves through this equation. So as time goes, the time derivative of the curve is the same thing as its curvature. So it is going to push it out in the directions that I've drawn here in this example. And this is called the curve shortening flow because it shortens length of the curve. And it follows from a result of Grayson in 1989, building on previous work of Gage and Hamilton, that if you start with a curve for which you can find a lift of, so a function beta from L to R, which lifts that angle, that unit complex number that I've mentioned in the previous slides, that e to the I beta. So this is a lift of e to the I beta. You need to be able to find such a lift if you have any hopes of deforming it to a straight line. So that's a necessary condition. And it turns out it is also sufficient for this flow to exist for all time and to converge to the straight line. So that's the result I mentioned. And so we will try to mimic this procedure in higher dimensions also through something called the Lagrangian mean curvature flow, where you replace the right-hand side by the mean curvature of a Lagrangian submanifold. Okay, so on this slide, I'll be telling you how to generalize these ideas to higher dimensions. So let's start with the Calabi-Yau manifold. So that's some extra structure that is needed. So you have the symplectic form, you have a metric, and you have then this omega. That's the thing that will be important for us, which is a complex valued n form. So n is a complex valued n form. Okay, just erase those things not to do. And they need to satisfy some compatibility conditions. So in particular, this metric is Ricci flat, but let's not worry too much about that. And then we have here a Lagrangian submanifold, which I'm going to suppose it is oriented. Okay, so oriented. And then what we will do is that we will restrict this complex n form. So let's just write complex n form. I restrict this complex n form to the Lagrangian. And then I have another n form, but a real valued n form on the Lagrangian, which is the Riemannian volume form induced by the induced metric. And both of these have unit norm, so they must differ by a unit complex number, which is this e to the I beta, which is then a function on the Lagrangian with values on the unit complex numbers. This is called usually the Lagrangian angle. And then we will define the special Lagrangians, which are our candidates to be the canonical representatives, as those for which this function is constant. So this is in direct analogy with what we saw happens for curves. Okay. And then, of course, if you have any hope of deforming an initial Lagrangian to a special Lagrangian, then this function here that you had here must be homotopic to a constant. So it must have degree 0. And so you must be able to find a lift from beta from this function to R. So that lift is usually called the grading, and the corresponding Lagrangians are called graded. And so everything I will mention is with respect to graded Lagrangians. Okay, and then the two questions are, is there a Lagrangian, a special Lagrangian representative of an Hamiltonian isotopic class? And if I have an initial Lagrangian, some L naught, and I pick a family of Lagrangians LT, which evolve through the so-called Lagrangian mean curvature flow, which is the flow where you substitute, it's the same flow as before, but this HT is defined also in higher dimensions. So in 2 dimensions is simply what we had before, but in higher dimensions is the mean curvature. And so the question is, does this flow exist for all time and converge to a special Lagrangian if it exists? And the answer to these questions is not known, but motivated by mirror symmetry that which we already saw in Linus' talk, in first talk. So there is a version of mirror symmetry which Lino did mention, And based on the predictions from mirror symmetry, Thomas and Thomas Yau posed two conjectures which try to answer these questions. So the first one is that, yes, there exists a special Lagrangian representative if and only if the Hamiltonian isotopic class of L is what is called stable. And the second is from Thomas and Yau, and it says that this Lagrangian mean curvature flow exists for all time and converges to a special Lagrangian if the Hamiltonian isotopic class of L is stable and the initial Lagrangian is almost calibrated. So let me write L naught, and L naught almost calibrated. Almost calibrated is actually was originally not part of the conjecture, but it was added after work of André Neves proved that the conjecture is wrong if you don't have that hypothesis as well. And almost calibrated means that the total variation of this beta is less than pi. So it means that if you take the supremum of beta minus the infimum, minus the infimum of beta on L naught, that's less than pi. So if you think in terms of the curves, that means that the velocity vector of the curves takes values in a half space. So if you have something like this, that's okay because the velocity vector, you see, never varies to the opposite side. But if you take something that does like that, then it's not good because you have this point here, and then you have this point here, and then you have this point here. And on total, this already gives you a variation that is more than pi on the angle that it makes with a fixed axis. And so that case is not totally, is not almost calibrated. So you cannot have this kind of stuff, but you could have this. And of course, the counter example that André Neves gave is in higher dimensions because of the previous result of Gage and Hamilton that I mentioned. Okay, so, and what I will finish my talk with is some results from last year, yes, from Jason Lotte and myself that give a positive answer to these conjectures in the four-dimensional case, assuming circle invariance. And part of the beauty of having this circle invariance and what makes it treatable is that we reduce most of our problems to curves and modified versions of the curve shortening flow, which allows us to then prove these results. And so, but let me tell you what the results are. The first result says that if you have a four-dimensional Calabi-Yau and a Lagrangian in it that is circle invariant, and if you further suppose that this Calabi-Yau has finite topology, so for example, H2, the second cohomology needs to be finite, and there are infinitely many examples of such Calabi-Yau manifolds and Lagrangian submanifolds, then indeed there exists a special Lagrangian representative of a given Hamiltonian isotopic class, if and only if that Hamiltonian isotopic class is stable. I say here S1 stable, and S1 Hamiltonian isotopic means that S1 stable means it cannot be destabilized by circle invariant configurations, but given that I didn't tell you exactly what stable means, that may not tell you much. On the left-hand side, being Hamiltonian isotopic to a special Lagrangian in the S1 sense means that you can use circle invariant Hamiltonians. And the second conjecture says that in the same conditions as before, and assuming the conditions of the conjecture, then the Lagrangian mean curvature flow exists for all time and converges to the special Lagrangian from the first theorem. And maybe given that I have 20 seconds, I will tell you maybe what stable is very quickly. If you have a Lagrangian, it is stable if you cannot break its Hamiltonian isotopic class, decompose it as a direct sum of two other Lagrangians with the average beta of the first one greater or equal than the average beta of the second. And I put average between these because it's the average of the exponential and then you take the logarithm. So the argument basically. And you may compare this, if you have seen, with the notions of stability for holomorphic vector bundles, and that's why I mentioned it now. And so now it makes sense to say S1 stable. Means that you cannot do this with L1 and L2 S1 invariant. Okay, thank you for the attention.
Oh, thank you very much, Gonçalo, for the talk.
Oh, I have a slide for this part. Okay.
And I don't know if again the questions from the audience, I don't know if they'll show up, but I would like to ask you one that has to do with previous slides of your results. So are these more geometric or more analytical results? You said that you can, in the end, reduce to the kind of curve shortening flow for some special, or for curves, but some kind of curve shortening flows. And there do you do analysis, or really the geometric part is the more relevant in these?
Yeah, so for the first result, there is almost, I think there is no analysis basically involved. It's very geometric and just playing around with curves and translating these notions of stability into what can be done in the circle invariant case. The second result, it involves a little bit of geometry and basically the input that we have gained from the first. And then it involves analysis for analyzing this version of the curve shortening flow. So there is analysis on the second, but on the first, no, there is only.
Let me add one regarding the second. So you still use the hypothesis of almost calibrated, although for the standard curve shortening flow, there is no need for that, right?
That's right.
And so, but here you do need it, right? If you don't,
yes.
If you don't have it, you want, you know of a counterexample, or it just.
I know Andres' counterexample actually works in this case.
I see.
Because there is an additional forcing term that appears that allows. Actually, I'll make a picture and I'll explain Andres' example with this picture. So. Let me try to see if I can do this. Something like this. Okay, so Andres' example is something like this. It's circle invariant, is in C2, but you can put then, if you have a symplectic manifold, you can cut off a piece like this and transplant it to very small to your manifold. So it will work in any case, but it's an example in C2. And the thing is that you have a curve like this that you draw in R2 using circle invariance. And this corresponds to circle invariance two-dimensional Lagrangians in C2. And then you have these ones in red that shrink down to a point. And then you have some other ones in yellow that are asymptotic to these lines that I've drawn here. And the problem is that these lines, the ones from these lines, they will collapse into the center before these red ones disappear. So the curve in blue must get contracted here before these things escape from there. Is that clear, more or less? Yeah. So the curve in blue must develop a singularity here in finite time. So that's the point.
I see.
Because these guys here, this part here is trapped. It cannot escape because of the pink curves.
Okay, Gonçalo, thank you very much. So this concludes the first half of this parallel session in geometry, which consisted of 3 talks of 50 minutes, which is a very hard thing to do. And I think we should congratulate the 3 speakers and congratulate the organizer for have chosen them to give such very good talks, 15-minute talks, which I think everybody got something out of any of them. Thank you very much to the 3 of you. And now we'll go to the second part of the session with kind of a plenary talk of this session given by Margarida Melo. Please, Margarida, you can share your screen.
Hi, everyone.
and Margarida, who is a professor at Università Roma Tre in Italy, and also a member of the Center for Mathematics of the University of Coimbra. And she will talk about, there we are, understanding the geometry of a compactified moduli space via tropical geometry. Go ahead, Margarida.
Yes. So thank you very much for inviting me. It's a really a very big pleasure. So I'll talk about this topic, which is one of my favorites. So I study algebraic geometry and moduli spaces and compactified moduli spaces. And when you study these compactifications, then it's natural that you find tropical geometry somehow. So that's the story I wanted to tell you. So I'll do that by starting from very basic considerations about moduli spaces, the things we like about them, and main examples. So, okay, remember, a moduli space is a parameter space for algebrogeometric objects with fixed invariance. And today, our main example is going to be MG, so the moduli space of smooth projective curves of genus G. So here you have genus 1 curve, genus 2 curves. And then, so most of the techniques that I will be saying really hold for lots of other moduli spaces. And one that I will also have in mind is moduli space AG of abelian varieties of dimension G. So remember, these are projective varieties which also carry on a group structure. And so I'll talk about techniques where we try to understand compactifications of these spaces via tropical interpretation of their boundary. So that's going to be the boundary of this compactification, if that's a good one. So that's the thing I want to explain. Okay, so actually, so the motivation for this is that, you know, often these spaces are endowed with an algebrogeometric structure. This is on the good side about this thing. On the bad side, we know that they are often not compact, not proper. So that's where the question comes in. So it's, of course, very good to have compact algebraic algebrogeometric spaces, so you can do integrals, for instance. But of course, you want to do a nice compactification, so you can work with this with your techniques properly. And for some spaces, this is possible. And then the most known case is MG. So this is, remember, MG is a quasi-projective variety, and actually, I will be thinking about MG actually as a stack. And it has dimension 3G minus 3. And for AG, this is again a quasi-projective variety or a stack of dimension G plus 1 choose 2. And so this is on the good side. So you can work with them as varieties. So they are algebrogeometric varieties themselves. But the problem is that they are not compact. So you can see this very easily for MG because smooth curves degenerate to singular curves. And for abelian varieties, this is even worse because you can lose by degeneration either your projectivity or the fact that you still carry a group structure when it's easy to build degenerations where both of these things will not be true anymore. Okay, so the dream situation, which would, you know, be that would maybe solve our problem, is that you can construct a modular compactification of your moduli space. What do I mean with modular? So modular is the key word here. So it's a compactification where the points of your compactified space themselves, they parameterize interesting algebrogeometric objects. And then you want a geometric condition to be satisfied, which I will say like this. So I want the boundary of your compactification to be well behaved. And one special case of this would be that in your compactified space, that the boundary of your compactification, usually write like this, it would be simple normal crossing, which means that you have something like the coordinate hyperplanes in a fine space locally. And then you want that so usually to compactify, you want to specify combinatorial data. And this combinatorial data maybe can be endowed with a tropical modular interpretation. And this is where the tropical geometry comes in. So what do I mean with this? So imagine that you in order to compactify, you want to add a certain number of things, and you are maybe able to give to these things an interpretation of some tropicalization of your original varieties. So this will be maybe clear later in the talk. And then the picture you can try to work is the following. So you start with your compactification of your, so this is going to be also for any variety, but the cases I will be treating are always moduli spaces. And if you have this nice geometric condition in the boundary, you can construct out of this the boundary complex of the boundary. So this is a complex where you specify so this is going to be something that will explain for you how does the boundary stratifies. So you construct a stratification of your boundary, and this boundary complex will carry the information of how these strata meet one with the other. And in the simple normal crossing situation, this is something classical. And recently, for the context I will be working with, this was also generalized to toroidal compactifications. Okay, so this is strictly geometric part of the picture. But then if you have also this thing, if you have also tropical interpretation, tropical modular interpretation to some combinatorial data, you can construct a tropical modular space. This is going to be usually a generalized cone complex. So it's going to be a complex of rational polyhedral cones whose gluing is going to be described by some category, usually. And if you have a nice way to describe the formations of your completion, then you can construct a tropicalization map. And this tropicalization map is going to be something that will be living in a certain category and give you a map, giving you a map from some space to this to the tropical modular space. So what one can hope in the end is that these two will be isomorphic. So let me explain. So this is interesting intrinsically. So you can work with this intrinsically, even if you don't have this thing. And you can, of course, use all your knowledge about the compactification to work with this independently. But the point is that if you have all of these, and if these are isomorphic, you can try to, for instance, compute the cohomology or understand the geometry of your compactification by using the tropical interpretation that you have here. And you know, the fact that you have a modular interpretation for the points of your variety is, of course, very helpful when you want to, for instance, compute integrals or compute invariants, this kind of thing. So this is the dream situation, which actually really holds very frequently. And this is the story I want to tell you. Okay, so let me recall about the Linge-Mumford's compactification of MG. So this is going to be the main character for the talk. So this is a parameter space for the Linge-Mumford stable curves. So what are stable curves? These are projective connected nodal curves with a stability condition. You have to ask for a stability condition if you want to end up with some separated finite type space. And you can say this like this. You want to ask that your curves in the limit, this will be singular and having several irreducible components, but you don't want them to be too wild, or you want to have control over them, and you can ask a condition like this. You want to ask that the automorphism group of your curves will be finite, but this can be said equivalently by asking that every irreducible rational component of your curve should meet the rest of the curve in at least 3 points. And then you ask for the infinitely many automorphisms of your irreducible subcurve, which is rational. Then with these 3 special points, you'll get just finite. You just get none out of there. And then the very big theorem due to the Linear-Mumford in the 60s that you know, that's that the moduli space MG bar, which is the parameter space of parameterizing this kind of curve, so stable curves of genus G. This is a projective the Linear-Mumford stack of dimension 3G minus 3. Projective means that it's the Linear-Mumford stack with coarse moduli space, which is a projective variety. So you get your compactification, and you get a nice compactification where the points in the boundary parameterize curves that you can easily study. And on the geometric side of the picture about the technical geometric considerations we did before, it's true that the divisor of the boundary, so mg bar minus mg, this is normal crossing. It's not simple normal crossing because the components of the boundary could have self-intersections, but it's normal crossing. And the theory now developed in a way that you can also work in this situation. And this divisor is topologically described by a category that I will now introduce, which is the category of stable graphs of genus G. And this is where, this is the thing that gives us the possibility to describe the boundary complex that I talked about in the beginning. So for that, let me remind you about the dual graph of a curve. So consider a curve in mg bar. So this is a stable curve, so nodal curve with several irreducible components. So we associate to each curve a graph, which is going to be denoted like this. It's going to have some vertices, edges, and a weight function in vertices. So the irreducible components of your curve will be mapped to vertices, and nodes will be mapped to edges in a way that if you have a node lying between the components xu and xv, then you're going to map your node to an edge, which is going to be an edge which is incident to the vertices u and v. And then you keep track of the information about the genera of irreducible components by associating to the vertices this weight function, which is going to be just associating to a vertex v the weight of the weight which will be telling you what's the geometric genus of the original component. So the example here, so start with a genus 3 curve and imagine that this degenerates to a nodal curve like this, for instance, by stretching these 2 nodes here and this one over here by creating these nodes like this. Then your dual graph is going to be just 2 vertices, which will be denoting for you that you have these 2 components, and with 2 edges connecting these 2 components, which would be these 2 nodes here, and the self node, so a loop, which will be telling you that this component has a self, as an internal node. And you keep track of the fact that this is still a genus 1 curve by saying that this vertex will be given weight 1. But for this, you just say that this has weight 0 because the fact that this has an internal node is already considered in the loop. So then you define the genus of your weighted graph by saying that the genus is just the first Betti number of your graph. These are always going to be connected. And then you sum the weights of your vertices. And it's very, and then you define for for a weighted graph a stability condition by saying that the graph is stable if for all vertices with weight 0, the degree or the valence of your vertex is at least 3. And then it's an easy exercise to see that the stability condition that you got in the beginning, that we said at the beginning, that would say that curve is the Linnemann-Mumford stable, is really equivalent to asking that the dual graph of your curve is stable. So the stability condition is completely encoded in a combinatorial way. And then out of this, we can describe the category of stable graphs of genus G, which is the category whose objects are going to be stable graphs of genus G. And morphisms are going to be given by weighted contractions. So what's these weighted contractions? Let me tell you in pictures. Watch this. So contraction is going to be associated by, is going to be given by choosing a certain set of edges, which would be empty, and then you would be also considering automorphisms. And then in a way that you map a graph to a contraction of this set of edges. But these contractions should preserve this rule, which is if you have an edge connecting two vertices like this contraction, which should be so contracting the edge into this vertex, should sum in the end the weights of the vertices where this E is incident to. And if you are contracting a loop, then the weight of the image vertex should be increased by 1. So with this rule, you see very easily that these contractions will preserve genus and stability. And then what we do is that out of a curve in this, out of a graph, sorry, in the category of stable graphs, you consider a locus inside MG bar, which is the locus of stable curves whose dual graph is isomorphic to your G. Okay, so for each stable graph, you consider this is going to be locally closed inside MG bar. And then the theorem is that you can use this category to describe the stratification of the boundary of MG bar. And what do I mean with this is that, so the whole MG bar naturally is going to be the union of all these locus. So the locus of curves with a specified low graph, this is trivial. But the important thing is that each of these locus is irreducible, and this is a hard geometric consideration. And the stratification part is going to be described by saying that in the closure, the topological closure of each locus is going to be given by union of smaller dimensional locus, which is corresponding to all MG prime, where G prime is a stable graph that has a weighted contraction to your G. So this means that the morphisms in your category are going to be telling for you how do you complete inside MG bar each of the strata. And then what we can do is that we construct a tropical modular space. This is going to be a cone complex, a generalized cone complex, as I said before. And this is going to be a modularized space for tropical curves. So a tropical curve of genus G is a pair given by a graph and a length function. So a graph for us is going to be just an object in GG, so the category of stable graphs of given genus. And the length function is just some association of real positive values to the edges of your graph. And then, given any graph, you can define a cone, which is the following. So you just give, you just parameterize with this cone all the lengths that you can give to such a graph. So you just associate to this the octant where you parameterize all the lengths that you can endow your graph with. And then you can construct MG trop, which is the following. So this is just encoding a very big limit where you consider all your cones and you glued your cones according to the morphisms in your category. Meaning that if you have an automorphism, you're going to consider a map here. If you have weighted contraction, you're going to have gluing of a face and everything. So this is just a very short way of indicating how you construct this space over here. And this has the structure of a generalized cone complex of real dimension 3G-3, and this was constructed like 10 years ago in joint work with Silvia Branetti and Filippo Viviani. And now we have a very beautiful theorem, which is due to Abramovich-Caporazzo-Payne, which tells you that actually these two spaces are so that the dream situation that I said at the beginning, that it actually holds in this situation. So let me try to explain what we have here. So on the technical side, we have a compactification, Mg inside Mg bar, which is toroidal. So it's not that you have a simple normal crossing compactification, as I said in the beginning, and it's not that you have a variety in the dream situation, but you have an inclusion of stacks. These are two stacks included one in another, where locally in the boundary, in the point in the boundary, what you can see is that points in the boundary are locally isomorphic to toric varieties, to a torus inside a toric variety. So this is locally this is as good as you wanted in the beginning. And then out of this, you can construct a space which is the Berkovich analytification of your space, because you have this situation here. And what's this space? This is a parameter space of completions of smooth curves over non-Archimedean field extensions of your original points. So this means that you start with some pointed family of smooth curves over a pointed disk, and you will be parameterizing here all the ways, so stable ways to complete this picture in Mg bar. And then you ask for this to be true over, so these parameter spaces are going to parameterize these over non-Archimedean field extensions. And this means that you will be having evaluation in your family. And then if you, for instance, if you construct something like this, you can then locally look at your degeneration and evaluate singularity here. And then this evaluation is going to give you a length function on a dual graph. So this is really giving you a way to go from so intrinsically, because you have a good compactification, you will be able to construct a very big space. So this space is going to be is a space where you can construct. So in this space, you would have like a generalization of all dual complexes of all normal crossings compactifications of your Mg. So this is just an ambient space where all of these dual complexes would live, and then you look at the compactification you are dealing with. So the way you describe the degenerations, and using the fact that this comes with evaluation, you can then construct a map to Mg trop. So this is called the tropicalization map. So let me write it here. So this is called the tropicalization map. And it really constructs out of a family, out of a family over puncture disk, and let's consider something like this. So this would be like a smooth family. You look locally to a singularity, then you would be looking in Mg trop to a node between two vertices, And you want to attach, remember, this is a moduli space of graphs together with lengths in your vertices. So the length you're gonna be attaching to the edge corresponding to the singularity you had in the beginning is gonna be given for you using the valuation. So the length of this edge would be the valuation of Fe if locally in the singularity that you had in the beginning, you would have a local equation given by this parameter. So this would be a local equation for the singularity. So this is really something intrinsic. That's my point. And then there's work by Thuillier and then generalized by Abramovich, Caporazzo, Payne in the setting of algebraic stacks with toroidal compactifications that constructs for you, give out of this analytic space a topological retraction P. So this is again something that is intrinsic. So this is a topological retraction. Right. Topological retraction from this big space. This is a big space of norms. And then you construct intrinsically a topological retraction to something that is called a skeleton. So this is the skeleton of your analytification. And this skeleton is actually, again, a generalized cone complex. This is a generalized cone complex. And then this breakthrough work of Abramovich, Caporazzo, Payne, they show that, that this is actually an isomorphism. So you really have that the topological retraction that you have intrinsically from the Berkovich analytification to its skeleton is actually an isomorphism with the tropical modular space that you had in the beginning 10 years ago. And then that's where we can start thinking, okay, so then this is a moduli space. So this parameterizes objects that we can describe, and then you can, start to compute homology classes and things like that. And can we translate back results to the original space? And the answer is that, as you can expect, is that you can in many, many situations. So let me tell you one. So one situation where this has been applied recently is that this can be applied to computing part of the cohomology of MG itself, not of the compactification. So the part of the cohomology of MG that we can compute is the top weight quotient of the Linz weight filtration of the rational cohomology of MG. So you know that so you can construct the Linz weight filtration for MG, because this is a quasi-projective variety. And the top weight class is going to have weight twice the dimension in this because of the properties of MG. This is smooth as a stack. And so the top weight degree of the cohomology, of the rational cohomology ring of MG, is going to be the part of weight twice the degree, which is in our situation 6G minus 6. And according to the Linz construction itself, you can show that the top weight part of your cohomology, where you compute degrees you have to adapt the degrees. This can be computed by the reduced homology of the boundary complex. So the top weight cohomology of your MG in degree 2D minus I is going to be given by the reduced homology of degree I minus 1 of the boundary complex of MG if you have a well-behaved boundary. So originally this was proved for simple normal crossings, compactifications in varieties, but as I said, This has been recently generalized for normal crossings, as we have in this situation, and also for when you have normal crossings and toroidal embeddings, which is the situation we have here. But then the isomorphism we had before, this isomorphism, will say to you, okay, but then the skeleton of this MG is actually identified with the link of MG trop. So actually, actually I should say here that here, this skeleton is not really, so it's isomorphic to the link of MG trop, where you just ask that all your weights are going to have total volume 1. It's just that, so this is a generalized cone complex, and you just intersect this with a unit ball or something like that. So this is called the link. And so because of this isomorphism, you can then compute this homology by computing the homology of your link. Okay, this is just because we have this. And then, you know, this is intrinsic, and but this is a modular interpretation. And so, in order to compute homology, you can, I don't know, you can try to use graph theoretical results or things like that to compute homology in certain degrees. And this is what I say here. So you can use tropical modular interpretation to help with computations. And this has been actually carried on to understand the topology of, to understand the top weight topology of MG in work by Chen, Galasius, and Payne recently. So let me just finish by saying that, so all I said can be, so I just told you the story about MG because it's easier and it's the first that we saw. But this is a strategy that can be applied in general. So each time you have, a nice compactification of an algebra geometric space, if you can understand the boundary in a nice way, you can apply this. This isomorphism. This is something that comes from the fact that you have a nice compactification to compute the top weight homology. And then maybe you can use, maybe if you have other tools like modular descriptions for these objects here, which could be very hard to understand, then you can apply this to understand the reduced homology using the modular description that you have. So this is what I'm saying here. So this strategy has been applied to understand other compactified moduli spaces. And one that I did recently is computing this for the moduli space AG that I talked about in the beginning. For this, the compactifications, there's not one canonical compactification as we have for the case of curves. But there are nice enough compactifications that are called toroidal compactifications of AG. This was constructed by Mumford, and they depend on some combinatorial data, which is an admissible face-to-face polyhedral decomposition of the cone of positive definite quadratic forms of rank G. So it's a long story, but out of such a decomposition, and there are some known decompositions, you can construct a toroidal compactification of AG. And then you can construct, again, a tropical modular interpretation for moduli spaces of abelian varieties, which would be just real torus of dimension G. And this decomposition here would give you the composition of your real torus in a polyhedral way, which is what you can imagine to be something with a tropical flavor. And then the good part about this is that for these decompositions, what you have is that sometimes you have nice decompositions, but the properties of your compactification are not very good. However, since we have the fact that this since we have that this map is intrinsic and this space parameterizes all of your compactifications, then you show that the topology of the links of different compactifications will actually be the same. So you can choose your favorite compactification, even though it's technical, even though it has not very good regular properties. Compute the cohomology of and compute the homology of the link in a way that will again give you information about the homology of AG itself. So even though geometrically you're choosing some compactification which is not well behaved and for which in the beginning maybe you could not apply the corresponding theorem, because you have in homotopy equivalence of your compactifications in this space, in this big space, you can choose whatever you want, and then in the end, your computations will be again valid for AG itself. So, for instance, we could show we could show for the first time that there's non-trivial odd degree cohomology classes for AG, which was something that was apparently not known. And we can also try to get like estimates for boundedness of some dimensions of homology classes and other kinds of results. So this is what I wanted to say, and thank you very much for the invitation and for listening.
Thank you very much, Margarida. And I do encourage the audience to ask questions if they want, using the chat of the question and answers system, which I don't know exactly how it works, but I don't see any message here. But I'd like to ask Margarida the following. So in terms of the moduli space MG, so you get this tropical interpretation kind of description of this moduli space, and you can recover some known, I guess, the known cohomology results about the moduli space MG from this tropical interpretation, or do you get some new results there?
There are some new results, actually.
I also, like here, because I noticed that for AG, you see clearly that this non-trivial odd degree cohomology was unknown for AG.
Yes.
You also get some new things about MG?
Yes. So yeah, this is not my work, but yes. So it's using this interpretation, you can. So actually, there's also another isomorphism that I didn't mention here. So this was also identified with Teichmüller, Kontsiewicz algebra for graphs, for categories of graphs. And using this interpretation, we could, so Shan, Glasses, and Payne, they could show some results that were well known, like boundedness of some cohomology classes, but also so that they did more than that. So there were also some results that were not known, not like I don't know by heart, but some there were computations where you could really say, for instance, say that HK of MG for K bigger than G or something like this is bigger than some lower bound that was completely unknown. Yes, so you really get new results. Yeah, and now also they could show also some conjectural non-vanishing results about cohomology of MG that were not known. But as far as I understood, this is being pushed further, and there are maybe new things coming through, and I think it's very beautiful picture. And
regarding AG, so it had been studied before, or
the cohomology?
The cohomology, yes, of AG, or you are obtaining kind of first results on this moduli space?
No. So what can be, so understanding the wall cohomology ring is something that is known just for G equal to 3 or something like this, but it's very well studied. So people study, people study like stable cohomology, and about stable cohomology, there are more things that we know. And there are lots of like spectral sequences that have been written to describe some classes. But the wall cohomology ring was known just until G equal 3, but for G equal 4, there's a lot known, but not completely. And then so our results were new from G equal to 5 until G equal to 7, and from G equal to 8 on, we just can get like some new bounds that were not known, but until G equal to 7, we can really compute the wall top weight cohomology, and there are also classes that we can describe that were conjecturally describing some classes in other compactifications, like in the Satake or Bailey-Borel compactification of AG. So I think there's a lot there. Like you get a new way to guess classes. So these odd degree classes, you cannot. They're not, of course, not easy to find because are not algebraic, but from this point of view, you have a real degeneration where these things make sense. So you can use this interpretation to exhibit new classes, and also there are other things that we cannot show, because from G equal 8 on, you just get like a really big number of cones, and it gets out of our hands to compute everything. But maybe you can guess that some pattern is true always, and maybe you can then try to get a way to prove that. So that's another thing that could be done as well. Yeah.
Okay, thank you very much, Margarida. I don't see any questions, so I'll wrap up this session, thanking again very much all the speakers for having accepted the invitation, for giving such nice talks, all of you. I'm seeing in order Pedro, Lino, Margarida, and Gonçalo. That's the order they appear in my screen. I also want to thank the participants who attended these lectures and have been here for this period of time. I hope you continue to enjoy the national meeting of the Portuguese Mathematical Society. Let me say that today at 5 p.m. we have a plenary lecture in geometry by André Neves, and I encourage you to attend all the lectures, but in particular this geometry one by André Neves today at 5 p.m. Lisbon time. Thanks to you all, thanks to the speakers, and I hope that very soon, with all the interesting things that have appeared using this pandemic and in terms of remote talks and so forth, and we saw that during this session, people using very nicely the technology that is available to us. But I do hope that we'll very soon be able to have meetings like this, geometry meetings, national meetings, etc., in presence, so that we can all interact directly with each other, discuss after the talks, discuss during the talks, and for me, at least for me personally, I really hope that we can get together very soon, all of us. Okay, thank you very much. Keep safe and see you around. Bye-bye.